Forces in motion. Imagine a playground. That playground is the playground of physics. Every activity done on that playground is related to physics, especially forces in motion. For example, let's look at that soccer ball rolling on the ground after being kicked by a kid. The ball is changing its position over some time. This is called motion. Motion is defined as the action or process of moving or of changing place or position. Okay, then what determines a motion?
Frankly speaking, motion can be described in terms of displacement, distance, velocity, speed, acceleration, and time.
Then what's the difference between distance and displacement, velocity and speed?
Good question. Displacement and velocity are both vector quantities, which means they have two characteristics, a direction and a magnitude. On the other hand, distance and speed are scalar quantities, which means they only have a magnitude. After knowing what motion is and its relationship with the 6 determining factors, let's jump right into the application of motion. The reason why we study physics is because we want to understand what is going on in this world. Like, why is the car covering a lot of distance by moving at a high speed? And why does a bullet land so far from its original position? That kind of things. Before trying to solve questions, we need to know the equations first. So here we go. These are the equations we have covered in this unit, and students are required to decide which one to use in different situations. And now let's take a look at an example. Let's say the circle is traveling towards another object at a constant velocity of 20 meters per second, since it's going right, for 5 seconds. If we know the circle's velocity and the time it takes to hit the object, we can simply use the equation d equals vt to calculate the travel distance. If we crunch in the number 20 times 5, it will give us 100 meters, which is the travel distance. On the other hand, there's another way to determine the change in displacement, and that is by graphing. Here's the displacement time graph, and as we know, the formula for the slope is rise over run. So in this graph, the rise is displacement and the run is time interval. So the slope here represents average velocity, and from the slope you can easily tell whether the average velocity over a period of time is constant. In a velocity time graph, the rise is change in velocity and the run is time interval. So the slope will be acceleration, and the area underneath will be the displacement. Another takeaway from this graph is you can also find the instantaneous velocity of this object right away by looking at the value of the corresponding y-axis. If the circle is affected by gravity, then the circle will travel parabolically, which means while the circle is moving forward, it's also moving downwards, and this process is known as two-dimensional projectile. In order to calculate two-dimensional projectile motion, the circle's motion needs to be broken down into vertical and horizontal components. This may sound a little bit counterintuitive, but Galileo discovered it a long time ago. He even took this revolutionary insight further and concluded that the curve of any projectile is a parabola. It was this idea that let us examine how two objects in a vacuum, even if of different shape and mass, will hit the ground at the same time, if both are dropped from the same height. And that's because they have the same rate of acceleration. So same experiment, but here we have another identical circle placed at the same height. Once they're released at the same time, from the graphs we can see that the two circles use the same amount of time to hit the ground, and we can use the equation here. And it will display negative 9.81. And acceleration is the same for both objects. Now we can break down the motion of the circle. In order to calculate the two-dimensional projectile circle, we break down the motion of the circle. In this case, the horizontal displacement will be the circle's horizontal velocity times the total amount of time taken to hit the ground, and this process can be described as dx equals vx times t. In order to calculate how far the circle has traveled downwards, we can simply calculate the vertical displacement by using the equation dy equals vit plus 1/2 at squared. To conclude, much of the development of classical physics has been based upon the advances in kinematics, and in modern day, the use of technologies allows scientists to conduct more accurate and precise measurement of motion. But the question is, how does motion start in the first place? Can an object move on its own?
No, an object cannot move on its own. Why? You need force. Okay, so let's go back to the soccer ball. How did the ball move in the first place? Well, according to Newton's first law of motion, an object will never change its motion until force is acted onto the object. So we can assume that some kid kicked the ball prior to this movement. They changed its motion from rest. In this process, the cause of the change in motion of the ball is the force being applied from your foot to the ball. So keep in mind that forces are a vector quantity measured in newtons. They are also the cause of the change in motion, and its description include its magnitude, its direction, the object on which it acts, the object that exerts the force, and the nature of the force. But at the same time, just because force is being applied to an object doesn't mean the object is in motion. For example, gravitational force can be applied to a box towards the center of the earth on a slant, but the ball won't move. Why? Because the reaction table from the slant is equal to the perpendicular weight of the object, and the friction force is equal to the parallel weight of the object. This represents a translational equilibrium. The overall force, the net force, is zero. We can illustrate this on a free body diagram. In a FBD, arrows must be drawn to scale. Because weight perpendicular is equal to force normal, and weight parallel is equal to friction force, they each must be the same length as each other. So then, what if the box is 10 kilograms and the slant is 15 degrees? What is the value of the normal force? We calculate like so to get around 95 newtons. But why is the reaction force equal to the gravitational force? Qualitatively speaking, it doesn't look like the table is pushing the box in any direction. Isaac Newton explained this in details. We've all heard about Sir Isaac Newton, the guy who summoned gravity, the man who ruined our dreams of flying. Well, sorry to break it to you, but Isaac Newton did not invent gravity, and neither did he discover it. Newton just formulated a theory about universal gravity faster than anyone else did. He also invented calculus. Along with his other world-changing discoveries, one of his most used and basic laws in physics is Newton's 3 laws of motion. Newton's first law of motion states that an object at rest or constant velocity will remain the same as the initial state until an external force is acted upon. Like mentioned before, a soccer ball would stay at rest until it's kicked. The ball goes on forever until friction is acted upon it. Another example will be if you are on your skateboard and your skateboard collides with a small rock, your skateboard would stop. But you, as a different physical object, tend to keep staying in motion since you're not attached to the skateboard. Newton's second law of motion. If force cannot be seen, then how can we measure it? Isaac Newton mentioned in his findings that force is equivalent to impulse over time. Because impulse is a change in momentum, and momentum is mass multiplied by velocity, and we know that mass stays constant, we can derive that force is mass times the change in velocity over time. We know that the change in velocity over time is acceleration, thus making the formula force equals mass times acceleration. From this equation, because force is proportional to the acceleration, we can find that the larger the acceleration is, the force increases in value. Newton's third law of motion states that when one body exerts a force on a second body, the second body simultaneously exerts a force equal in magnitude and opposite in direction on the first body. This occurs in almost every force applied in nature. There are many different types of forces, including a few of the most used kinds of force. Weight. The weight is not the mass of your body. Weight is the gravitational force you have on your body down towards the center of the earth. The scale you use to measure your mass is actually measuring your gravitational force to later on calculate the mass of your body. On a free body diagram, it is pointed from the object to the center of the earth. Normal reaction. Due to Newton's third law, we know that any contact between objects will repel the same amount of force in the opposite direction. It is drawn perpendicular to the contacted surface. Tension force. The tension in a string or a rope is measured from its tautness. It is a pull force from a rope or string to the object. Solid friction force refers to the force generated by two surfaces that are in contact and slides against each other. Friction force is always in the opposite direction of the object's motion. We can calculate solid friction using friction force equals coefficient of friction times force normal, where the coefficient of friction depends on either the static or dynamic phase. Static friction is what keeps the object stationary until a sufficient amount of force is applied, measured with static friction force equals to the coefficient of static friction times force normal. Fk is equal to the force applied until pushed over the limit of Fk max, where the friction force will dramatically decrease to a constant dynamic friction. As mentioned before, dynamic friction is the force of friction opposite to the object's motion. In the previous example, we can determine that the parallel weight of the box is smaller in value than the static friction force, which is why the box is motionless. Overall, by using concepts of physics such as forces in motion, we are able to determine a certain upcoming occurrence from a set of valued information regarding that prediction. These revolutionary concepts help lighten the unknown. If these ideas are applicable throughout the universe, and if a person or machine were to know every atom's position and motion, is it possible to accurately predict or calculate the future? That would mean that every action, accident, and decision are all already set and unchangeable. Everything would be inevitable. Speaking of inevitability, the end of this video is unavoidable.